Yeah, okay. Well, thank you everyone in the audience for coming today. I am Dr. Edward Bryant, and I'm a Astro Prize Fellow at the University of Warwick. And what that means is I spend my days looking at a computer, but then looking at data from telescopes that are looking up at the sky, and looking for new planets and looking for planets. And what I'm here to tell you about today is I'm here to tell you a tale of dwarves and giants. Now, don't worry, this is a space lecture. This is an astronomy talk. This isn't a fantasy telling of a novel. What I mean by dwarves are these. If my slide's going to work. There we go. Red dwarf stars. So red dwarfs or M dwarf stars. These are very small stars that are between half the size of the sun all the way down to only a tenth or 20% the size of the sun. So these are very, very small red stars. And by giants, what I mean are giant exoplanets. So these are exoplanets are any planet orbiting a star that isn't the sun. So these are planets out in the galaxy around distant stars. And by giant exoplanets, I mean any planets that are similar in size to Jupiter or Saturn. So these really large, gaseous giant planets that we have in our solar system. And the reason why I'm going to tell you this story is because what I spend my days doing is looking for these planets, and then studying their overall populations. So looking at not just individual planets, but the whole demographic of planets, and using these populations to try and answer some really interesting questions about the galaxy. As Imo alluded to, the question in particular for today is how do planets form? But before we can understand how planets form, first we need to understand how do we find an exoplanet. And so you might think, well, we can just look up in the sky. That's how we found some of the planets in the solar system, how they were found many, many years ago, is they reflected light from the sun, and ancient astronomers were able to look up and see them. But it's a bit harder for exoplanets. And the reason it's a bit harder is if we were to look at this image here of just a street lamp, and I was to tell you that there's a moth really close to this street lamp, you can't see the moth. And the reason you can't see the moth is because of the glare from the lamp. The light is too bright and the moth is too close, and so the moth is just swamped out by the light, and you can't see anything there. And the same thing happens with exoplanets. Their stars are so, so bright, and their stars are so far away, that what that means is that the exoplanet itself is just swamped by the light from the star. So we can't see them at all. We can't see these planets directly. So if we can't see them, how do we know they're there? And so to explain that, I'm going to show you an image of a field. And the reason I'm showing you a picture of a field is because I'm sure many of you in the audience immediately would have known that a person walked through that field. You can't see the person, but you can see the footprints they've left behind. If you were to look a little bit closer, maybe at the size of the footprints, then you might then be able to tell how big their feet are, how big the person was. If you got really up close into one of those footprints and looked at the pattern on the floor, you might even be able to tell what shoes they're wearing. And the reason why I'm telling you this is because you can tell an awful lot about what happened here based on the impact the person left on the environment. You can't see the person, but you know they were there. And we use similar methods to find exoplanets. We can't see them themselves, but we can look at the impact they have on their environment, or in the case of planets, their host star. And so the first method that we use is something called the transit method. So this is where a planet passes in front of its star as viewed from our telescope. And when the planet passes in front, it actually blocks out some of the light coming from the star. So if I'm now going to show you a video of what happens, and if we're monitoring how bright a star looks, as the planet passes in front, the star appears to become slightly dimmer. And then if you have a larger planet pass in front of the same star, the star becomes even dimmer. It blocks out more light. And so if we use our telescopes to measure how bright a star looks, and we get these brightness measurements over a period of weeks or months, what we may see is some repeated dimming events. So if I'm now showing you what this looks like in terms of the data, if we have the brightness of star against time, you see these periodic dimming events going on as the planet passes in front of the star, as it blocks out some of the light. And then if we continuously monitor this star, what we'll see is these repeated events where it's the difference in time between these events tells us how long that planet takes to orbit its star. So you see this planet only takes one and a bit days to orbit its star. It's very, very close to its host star. And the depth of these transits tell us how big that planet is relative to its host star. Um, And so the way we look for these transits, these transiting planets, is by using transit surveys. So transits themselves are quite rare, as I'm sure you can imagine. The planet actually needs to be orientated in its orbit such that it passes in front of the star. What this means is that for many, many planets don't cause transits. So to find some planets, we need to look at lots and lots of stars. And we do these with, for example, the NGTS Next Generation Transit Survey. Now, this is a survey that I work with myself, and I thought it might be interesting as well to actually see some of the hardware. This is a real picture of the NGTS telescopes. They're in an enclosure in the middle of the Atacama Desert down in Chile. And all these telescopes are continuously looking at the sky when it's dark, looking for transiting planets. But as well as using telescopes on the ground, you can use telescopes in space. So this is an artist impression of TESS, the Transiting Exoplanet Survey satellite. This is a NASA mission that's up in space, and we can use, and this mission is also continuously observing the sky, looking for transiting planets. Now, as I said, from the transit events, what you get is the diameter of the planet, how large it is. But what you don't know is how massive that planet is. And when we're interested in understanding how planets form, understanding their mass is very important. And so we have another method that we can use to measure the mass of the planets that uses something known as the Doppler effect. And I forgot I had an image here. We'll go to the Doppler effect. But anyway, yeah, this is an example of one of the images that we see from these telescopes. And you can see that each dot here is an individual star. So this is a single image taken in time, and you have thousands of thousands and thousands of stars in this one image. This is a real image from the TESS space mission. And so we get lots of these images, and we can look for transiting planets. Now, I was getting ahead of myself earlier, but we can now move on to the Doppler effect. So the Doppler effect is something which I'm sure everyone in the audience has experienced, but some of you may not know what it is or why it happens. And to explain why it is, I have a cartoon of an ambulance. And the reason I have a cartoon of an ambulance is this is the scenario where I imagine most of you will have encountered this effect. And so what the circles emanating out from this ambulance is our reputations of the sound waves from the siren. So when a siren's making noise, the waves are emitted and the sound waves travel at a uniform speed in each direction. But the way our brains hear sound is the pitch is related to the spacing between each wave. And so as the waves are emitted the same in each direction, if the ambulance is still, then the siren sounds the same wherever you are. But if the ambulance moves, something very interesting happens. So if I now move the ambulance across the slide, you can see that while each sound wave still is emitted uniformly in each direction, due to the motion of the ambulance, the sound waves behind the ambulance appear to be further apart. And so if you're stood behind the ambulance and it moves away from you, the siren sounds deeper, it sounds lower in pitch. And if you stand in front of the ambulance and the ambulance is coming towards you, then those sound waves appear to be compressed together. And what that means is that the siren, you hear it at a higher pitch. And this is why as an ambulance comes towards you and passes you down a road, the siren appears to change pitch, change sound as the ambulance moves past you. The siren itself is making exactly the same sound. It just appears different because of the motion of that ambulance. As we move it, it compresses or expands the waves. And as well as sound, the same thing happens for the light from stars. So if I now have two stars here being observed by a telescope, they both look a similar color. They both look roughly yellowy, sort of an orange color. This is the color that our sun appears to be. But if we move these stars now, one towards the telescope and one away, the star that moves towards the telescope, the light waves appear to be compressed. And so the star appears to be ever so slightly bluer. And if the star that moves away from the telescope, the light waves expand slightly or appear to be longer in wavelength. And so the star appears ever so slightly redder. And the reason why this is important for exoplanets is because Alice does play. So when a planet orbits a star, the planet doesn't just orbit the star. The star and planet both orbit the center of mass of the system. And what that means is while the planet is orbiting, so is the star. The star is doing a small orbit or a little wobble during the orbit of the planet. And so if we have our telescope down the bottom looking up at this planetary system, the speed of the star the motion of the star towards or away from the telescope, known as its radial velocity, appears to shift, appears to change. And the impact of this is if we can observe and try and measure what color that star appears to be, it will change during the orbit of the planet. Whereas when the star moves towards the telescope, it appears slightly bluer, and when the star moves away from the telescope, it appears slightly redder. And if we measure what color that star appears to be, and we measure how that changes during the orbit of the planet, that can tell us how quickly the star is moving, and the speed at which the star is moving in its little wobble orbit is related to how massive the planet is. So by measuring the change in color of those stars, we can actually weigh planets. We can measure how massive these planets are, and we can learn what they're like. So we now have our two methods, the transit method, which we use to find these planets, and we can find out what their diameter is, and then this radial velocity Doppler method, where we can measure how massive these planets are. So what are these exoplanets like? Using these methods over the past sort of few decades, astronomers have found thousands of exoplanets orbiting stars outside the solar system. But are they like the solar system, or are they something completely different? So I'm now going to, briefly show you the population of planets we found. And I'm going to show you these planets plotting on the y-axis here will be the mass of the planet in units of the mass of the Earth. And along the bottom will be the distance from the planet to the star as a function of in units of the distance from the Earth to the Sun. So these markers here are showing you the locations on this plot where some of the solar system planets would be. So we have Earth down here, with Venus very close to it in terms of mass and distance. We have our gas giant planets up here, Jupiter and Saturn, and down here we have the ice giants, Uranus and Neptune. And if I now plot on the exoplanets we found, they're here. So they're very unlike, they're not at all like the solar system planets. One of the first things we found very quickly after finding these planets was that the solar system is not the prototype for all planetary systems. These are very different systems and very different planets. The first thing that immediately jumps out is that the vast majority of the planets we found are 10 times closer or more to their star than the Earth is. These were really, really hot, really, really, really inhospitable hot planets. For example, we found some planets that are similar in size to Earth, but we think are so hot their surfaces are covered in lava and magma oceans. We have planets up here, this sort of clump of planets up here, is planets similar in size to Jupiter that we think are really, really hot. So we imaginatively have called these hot Jupiters. And so these are Jupiter-sized planets that, again, are so close to their star. They're 1,000 degrees or more. They're really, really hot planets. And we even found one planet called WASP-76 that's so hot, it's hot enough that iron can actually vaporize and form clouds on the hottest part of the planet. And then this iron can actually condense on the cooler parts, and you have iron rain. Iron is raining out in the atmosphere of this planet. But as well as these planets, we've also found a planet called Bebop 1b, which is orbiting two stars. So instead of orbiting one star, this planet is orbiting a binary star system, and then the planet is orbiting around both. And so if you were on this planet, you might see a double sunset or a double sunrise, reminiscent of Tatooine from the Star Wars films. So so as we were saying, these planets are completely unlike anything we see in the solar system. And so by looking at them and by looking at all these every time we find a new planet or we find a new system, we learn something new about the galaxy. Because originally, if you go back before we found the first planet, if you go 30, 40 years ago, our knowledge of how these planets formed was based on the solar system. That was all the data we had to calibrate our theories to. But now we have thousands of systems and thousands of planets. And what they're telling us is that we need to improve our theories to understand how these planets form. And that's what I do. I spend my days, I say, looking for these planets and measuring their populations and trying to use these overall demographics to understand what happens to these planets. How do they form? How do they evolve? And how does their host star interact this? As I say, the question that mainly underpins the work that I do that I'm going to talk about now is how do giant planets form? How do you form this huge ball of gas with a nice rocky core? How do you form this planet? And so we do know very easily where giant planets form. And giant planets form in what's known as a protoplanetary disk. So this is an image from the Alma Observatory of a protoplanetary disk. So right at the center of here, in this bright yellow spot right in the middle, will be a very young star. And surrounding this star is this huge disk of gas and dust and rocky material and icy material. And it's within these protoplanetary disks that planets are born, that planets form. And our main method for how we think these planets form is a method known as core accretion. So what happens in core accretion is, and I'll go into a nice cartoon, we have the red cloud is sort of representing the gas in the disk, and these black circles are sort of the rocky, dusty particles. And these are all moving around in the disk and all moving in different directions, and they collide and combine together to build up a protoplanetary core. And these cores can grow to be very, very massive indeed. Like these cores can grow to be 10, 20 times the mass of the Earth. These are very huge, very large, rocky objects. And when they become this large, they begin to accrete large amounts of gas from the disk. And they accrete this gas and it forms an envelope around the core, and that forms your giant planet. So that forms your Jupiter-like planet from this disk. And this theory works well for explaining how you form the solar system planets, and it worked well for explaining how you form some of the earlier planets that we found as well. But the interesting thing for my work is what happens when you make your star smaller. Because we believe and we know from some observations that if you have a less massive star, you have a less massive disk. And if you have a less massive disk, then that means you have fewer building materials, less of this rock and dust and ice, fewer of these materials available to form your giant planet. And so the theories predict that it should become much, much harder as you go to a smaller, less massive star to form these giant planets. In fact, some of the theories predict that once you get down to maybe 30 or 40% the mass of the sun, it should become impossible to form these giant planets through this mechanism. There should just not be enough material available to form these planets. Which then brings us this other question, is can these small stars form giant planets? And as I said, I am an observer, so I look at the populations. And so the question that I answer to try and answer this question is how common are giant planets, or how rare are giant planets around small stars? So of course, if we look at loads of these small stars and we find loads of giant planets, then that means these stars are very, very good at forming these planets. And so we need to update our theories. If, however, we look at these stars and find no planets at all, then that's good for our theories. That means these planets can't form around these stars. So this is what I want to do. This is what I wanted to do in my work, was to go out and study these stars and try and study their planetary populations. But how do I do this? So if I want to perform a planet census, if I want to know how common planets are, I need to find lots and lots of planets. But as I mentioned, we expect these planets to be very rare. And also due to the fact that we need transits in order to find them, we need to look at lots and lots and lots of stars in order to find planets we need. And so we need somewhere where we can get a huge amount of stars. And we get these stars from the TESS mission that I mentioned earlier. So the reason why TESS is really great for this work is because, as you can see from this image on the left here, TESS has these 4 cameras, which are continuously observing the sky in sort of this footprint that you can see on the right. So you have this map here where you have 1, 2, 3, 4 cameras laid out in this strip. And then what TESS does when it observes is it will observe one strip and then will rotate and observe another strip and another strip of the sky and another strip of the sky for 27 days at a time. So in 1 year, it will observe one hemisphere of the sky. And then it repeats this process for the other hemisphere. And what this means is that through the observations of TESS, we have the sort of brightness monitoring of stars across the entire sky. So we have a huge number of stars available to us, the large number of stars that we need to be able to go and find these planets in large enough numbers that we can measure their population. And so that's what I did. So how do you find these planets? Well, exactly what do you do what is the pipeline and process for hunting for these planets? So I start off with obviously my light curves from TESS, and then what I do is I pass these through computer programs and computer algorithms. So I could look through these by eye, but that'd be very time consuming. and it would take far too long. I would still be looking through them now. So I use computer algorithms which look for these transiting signals and then perform additional checks to confirm whether this is a planet or something hiding, masquerading as a planet. For example, two stars orbiting each other can sometimes mimic as a star and a planet. And having applied all these algorithms and these tests and working out what these planets are like, hopefully I will have found lots and lots of planets. But did I? Did I find any planets? And that's the key question, because remember, these planets are expected to be very rare. These planets maybe even aren't expected to be able to form. So did I find any? Yes, I did. So this is now again showing what this is now showing is the planets that I found as the purple stars against sort of the population of other planets known from other surveys in black. And what we're now showing is the radius of these planets, or the half the diameter of these planets, where the units are the radius of Jupiter. And on the bottom is the mass of the host star in units of the mass of the sun. And so Jupiter would sit about here in the diagram, 1, 1. And what we're seeing is that these planets that I found are similar in size to Jupiter, but their host stars are much, much less massive than the sun. And in particular, these 4 planets down here, these are very, very exciting planets. And the reason these are exciting is, as you can see down at the bottom, the host stars for these planets are between 20 to 40% the mass of the sun. And as you remember earlier, these are planets that shouldn't be able to form. These are huge, monstrous systems. And this is showing a sort of an artist's impression of what one of these planets might look like. These planets, their radius is only a quarter or a half the radius of their star. For context, the Earth is 1/100th the radius of the sun. These are ridiculously large, monstrous systems which should not have been able to form. But that then begs the question of how did they form? And as I mentioned, in order to answer how they form, we need to understand how good these stars are at actually forming these planets. Are these planets the true exceptions, or are they indicative of a large population? And so to do that, as I mentioned, I need to measure the population size and how common these planets are. And to do that, I first need to ask the question of, did I find every planet? Because of course, if I want to know how common these planets are, as well as knowing what planets I did find, I also want to know what planets I missed. And it's very likely that I missed some planets because the data is imperfect, the computer algorithms I used are imperfect, and so we will miss some planets. But it's very, very hard, as I'm sure you can imagine, to try and know how many planets you haven't found. It's because you haven't found them. So what we need to do is we need to start off with a scenario where we know how many planets there are to begin with, and then we can know how many we found. And the way we do this is by simulating those planets. So this is performing something known as an injection recovery test. And what we do is we start with sort of real test data here on the top. So this is all showing real data from tests, which is just a flat line. And then we use our knowledge of what transits look like, what transits are produced by which planets, and simulate a transit-like model. And then if we combine these two together, we get our transiting light curve. So this is our simulated transiting light curve of a planet that we might be interested in finding. And we repeat this thousands and thousands and hundreds of thousands of times for lots and lots of stars. And so now we have a population of planets where we know exactly how many planets there are. And so if we pass these through the same algorithms that we used before, we will then know exactly how many simulated planets we found, and will also, most importantly, know exactly how many planets, and crucially, which planets we've missed. And so we then combine all this together to then estimate from our initial search how many planets we haven't found from our survey. And so combining these together, we finally have all the steps we need to perform our census. We've looked at nearly 100,000 stars, data from 100,000 stars with tests, found a whole load of giant planets, and we also know how good we are at finding these planets. And so if we combine these all together, we can answer the question at the top of this slide about how common these planets are. So what I'm going to show you on this graph is sort of the occurrence rate of these planets, so how common they are on the y-axis in terms of the number of giant planets per star in a percentage. And then on the bottom, we're showing the mass of the host stars, again in units of the mass of the sun. And if I now plot on my results, this is what we have. So compared to stars, giant planets around the sun, shown by the blue and the black point in the top right-hand corner, the planets around these low mass stars are very, very rare. They are much rarer than planets around the sun. And this is what we expected from the formation theories, that these planets should become much harder to form. They should become much rarer. But again, what we didn't expect to see was that the population down at these very low mass stars, 20%, 30% the mass of the sun, there is still a population of planets there. These planets do exist. And that is that very exciting population that we want to try and understand better. So let's go back to our questions we started with, and have we answered these? So our first question, how common are giant planets around small stars? They are very, very rare, but they do exist. And then, can small stars form giant planets? Yes, they can, but not as well as stars like the sun. They still find it much harder to form these giant planets. But as I mentioned, these stars weren't expected to be able to form giant planets. So that now leaves us with the final question of how do small stars form giant planets? And we have some ideas for how they might be able to do this. As I mentioned, the major stumbling block we have to be able to form these planets is the amount of material available in the protoplanetary disk. So maybe there's just more material available to form these planets than we initially thought. And there's a couple of reasons why this might be. And the first of which is the fact that stars are born in giant clouds of gas, such as the one on this slide, known as nebulae. So this is showing a picture of actually the Orion Nebula, close to the Orion constellation. And what we have here is that all these dots of these red dots and these small white spots you may be able to see, these are all new stars. These are stars that are forming out of this cloud of dust, because a cloud of gas, because this is where these stars form from. But what that means is when these stars are very, very young, they're still enshrouded in this cloud. We can't see them. We can only begin observing these disks and measuring how much material is in these disks once they're already a few million years old, by which stage the formation of these planets could very well be very underway. And there's some work that's beginning to suggest that when these stars are very young and these disks are very young and we can't observe them, they are much, much more massive than they are by the time we can observe them, sometimes up by a factor of even 10. And so this means it's very possible when these disks are very young, there might be more material within them, and potentially enough to form these giant planets, even around these very small stars. The other possibility is that maybe just some disks are much better at forming a giant planet than others. If you go back to the occurrence rate results I showed earlier, for these very small stars that are 20% the mass of the sun, we'd expect maybe only one planet for every 1,000 stars. But for stars that mass, we've only looked at a few tens of disks. And so our theories for how good these stars are at forming planets is just based off the amount of material available in these disks. But it could be that there are some disks that we haven't looked at yet that have a very particular and very special combination of characteristics. They could be slightly larger. They might have a higher proportion of rocky material to gas in them. They might live for slightly longer and so have more time to form the planet. All this combines together to potentially that maybe none of the disks we've observed yet would be capable of forming a giant planet. But they don't need to be, because as I say, we've only observed a few tens, but only one in every 1,000 stars has one of these planets. And so maybe we just need to keep observing more and more disks until we get lucky and find the one disk that can explain where these planets come from. But the last possibility is that maybe these planets just form through an entirely different mechanism altogether. As I said, the mechanism that's sort of underpinning the predictions for this is that these planets form from the bottom up, from this material colliding in the disk and forming the giant planet. However, potentially there's another mechanism that's been theorized as being possible, which is that these disks themselves are actually very unstable. And so what this image at the back is showing is a simulation of this process, where you have the star is this white dot right in the middle, and then the red and the green and the yellow is actually showing a protoplanetary disk that's becoming unstable and is sort of fragmenting under its own instability. And if it fragments in just the right way, it can collapse and condense to form these two white spots here, which are planets. It can potentially collapse and directly into these giant planets, can form directly out of this disk. And while there's still a lot of work being done to understand whether these disks are able to fragment in the right way to form these planets, what has been shown is that if these disks can fragment, they are very, very good at forming giant planets, even around the smallest stars. So that brings me now towards the end of my tale of dwarves and giants. So just sort of go through what we've done so far. We can find exoplanets, planets around stars other than the sun by observing the impact that these have on their host star, by looking for these transit events or looking for the change in the color of these stars due to the orbit of the planet. Using these methods, we found thousands and thousands of exoplanets, which are nothing like anything we've seen in the solar system at all. These are very strange, very new, very weird objects. And by looking at these planets and studying them and their populations, we can learn things about our galaxy, about how these planets form and evolve that we would never have expected before. The key one of which for this talk is that small stars, the smallest stars, can form giant planets. But what's the next chapter of our tale? Where do we go from here? What's next for understanding these systems? And what's next for understanding these systems is JWST. So this is the new NASA flagship satellite up in space. And what this satellite does for exoplanets is a technique known as transmission spectroscopy. So what this is what JWST does is it looks at stars and it measures what's their spectrum. So this is how bright a star looks across different wavelengths of light. But in particular, we can observe the light coming from a star as the planet passes in front. So you have the planet here at the back and the star here at the front. What you can see is that this thin ring around the outside of the planet is its atmosphere. And so what JWST does is it observes the light that's passed through the atmosphere of the planet. And what this does means is then these different molecules, such as water or carbon dioxide or carbon monoxide, in the atmospheres of these planets, absorb light very, very specific and very particular wavelengths. And so what this means is by looking at the light coming through these atmospheres, we can actually detect what molecules, what gases are in the atmospheres of these planets. And so this is an example for a gas giant WASP-39b. And so you can see this is showing on the y-axis is how much light has been blocked out as a function of the wavelength. And so you can see these peaks due to different molecules in the atmosphere. So this large peak here is due to carbon dioxide in the atmosphere of the planet. There's some signs of water as well in the atmosphere of this planet. And so by looking at the atmospheres of these planets, using JWST and learning what these planets are made of and exactly what their compositions is, this can give us some of the final clues we need to actually work out which of these theories is telling the truth. How did these planets form? What are they made of? What are their atmospheres like? How large are their planetary cores? And so this really is the next step for these planets and these really exciting systems, is trying to observe them with JWST, trying to learn what they're made of, and really trying to understand how they formed. But just in terms of what's next for exoplanets as a whole, as you may have noticed from the earlier slide, there's no planets down here. We haven't found any planets similar to Earth or Venus or even the ice giants. We have a few similar to Jupiter, but none down here. And this probably is not because our solar system is unique. It's because our current methods and our current telescopes aren't sensitive enough, aren't good enough yet to detect these planets. The signals from Earth are tiny, very, very small signals that we can't see yet. And so the next step in terms of the next few decades for exoplanets overall is to try and find Earth 2. And there's a few missed telescopes that will hopefully be launching over the next years and the next decades that will enable us to do this. There's the Plato mission, which is currently a lot of the design and planning for this mission is led from the University of Warwick right here in the UK. And one of the main primary goals of Plato, so Plato will be a transit survey mission like TESS, like NGTS, but one of the main goals of Plato is to find an Earth analog, to find an Earth-sized planet in a 1 year orbit around a sun-like star. And there'll be a follow-up to Plato in about 15 to 20 years' time called the Habitable Worlds Observatory. And this telescope is aiming to build on JWST to again look at the atmospheres of these planets, but with a potential to try and look for what are known as biosignatures or biomarkers. These are potential combinations of molecules or combinations of gases in the atmospheres of these small Earth-like planets, which could potentially be indicative that there is or was once life on these planets. And so that is where exoplanets as a whole is going over the next 10 to 20 to 30 years. So it's a really, really exciting time in the field of exoplanets, both to be involved in it, to be looking in, or to potentially be a sort of secondary school student in the audience who might be able to be working with these telescopes and with this data in a few years' time. But with that, that brings me to the end of my talk, the end of my tale of dwarves and giants. So I will thank you all very much for listening. Thank you for your attention.